So welcome everyone to the December version of the Statistics Former Student Network. We're very fortunate to have with us today Dr. Eun Sug Park. Dr. Park is a senior research scientist at the Texas A&M Transportation Institute. She received her PhD in statistics from Texas A&M University under advising by the late Clifford Spiegelman. And prior to joining the Texas Transportation Institute in 2001, she was a postdoc at the University of Washington's National Research Center for Statistics and the Environment. Her areas of research include environmental modeling and assessment of health effects of air pollution mixtures, source apportionment by multivariate receptor modeling, latent variable models and factor analysis, Bayesian hierarchical modeling, and model selection and transportation statistics. Her research has been funded by the National Institutes of Health, the Health Effects Institute, and the Federal Highway Administration. Dr. Park is a fellow of the American Statistical Association, elected member of the International Statistical Institute, member of the TRB Statistical Methods Committee, and editor of Chemometrics and Intelligent Laboratory Systems. She also was the recipient of the famous H.O. Hartley Award in 2023. So welcome, Dr. Park. We are looking forward to your presentation. Go ahead, take it away.
Thanks. First of all, I'd like to thank Marcy and Anna for inviting me and organizing this webinar. Let me say a few more words about myself. I graduated in 1997, and since my graduation, I've been working on many different real-world problems for over 25 years. And I have been collaborating with scientists and engineers from different disciplines. Two of my current main research areas are transportation and air pollution epidemiology. And today, I'm going to talk about some of my air pollution epidemiology research. Before I start, I'd like to acknowledge my PhD advisor, Cliff Spiegelman, who passed away in 2020, for guiding me into environmental research and teaching me the value of learning science and substantive knowledge. I'd also like to acknowledge my current collaborators. Elaine Szymanski is an environmental epidemiologist at Baylor College of Medicine, and we have been collaborating for over 15 years. Chang-Woo Lee is a statistician. He worked as an RA for my NIH project when he was a PhD student at A&M. He graduated in May and is now a postdoc at Duke. Phil Hopke is an environmental scientist and a pioneer in receptor modeling. Don Kang is a transportation engineer at TTI. Marco Benedetti is a statistician at the National Highway Traffic Safety Administration. And Mansuk Oh is a statistician at Ewha Women's University. It has been a privilege for me to work with all of them. The research I present today is based on joint work with this great team of collaborators and is currently being supported by these two NIH grants. I'll talk about two separate but related problems today: identifying pollution sources and their contributions to pollution based on ambient monitoring data, and assessing health effects associated with those sources. Here's the outline of my talk. Because this will be an overview talk for source-specific exposure assessment and health effect evaluation, I'll skip most of the technical details. For those of you who have never heard about these topics, I'll start with some background for this research and give an overview of an air pollution forensics tool called multivariate receptor modeling, along with associated challenges. Then I'll talk about previous approaches to multivariate receptor modeling at one monitoring site and recent developments for spatially extended multivariate receptor models that are more relevant for source-specific exposure assessment in air pollution epidemiology studies. I'll also describe some Bayesian approaches that can be used for source-specific health effects evaluation, including a recently developed scalable two-stage Bayesian approach, along with the application to Harris County birth outcome data and close with a summary and discussion. Okay, background. Why source-specific exposures? We all know that air pollution is harmful. By the way, source-specific air pollution means emissions from specific sources. For instance, emissions from transportation sources, emissions from power plants, or emissions from refineries. Traditionally, the health effects of air pollution have been assessed one pollutant at a time. For instance, the effect of NO2. It is called pollutant-specific health effect evaluation. However, we live in a multi-pollutant world, and the air we breathe is a complex mixture of many pollutants, including particles and gaseous species from different sources. Also, it's now recognized that the toxicity of pollution depends on pollution sources. So by characterizing multi-pollutant exposures through source-specific exposures, we can evaluate the combined effects of many pollutants due to individual source types, and consequently, more targeted enforcement strategies controlling harmful pollution sources can be developed. The main challenge with source-specific exposure assessment is that source-specific exposures cannot be measured directly. Instead, they must be estimated based on multi-pollutant data measured from ambient monitoring stations by source apportionment methods, such as multivariate receptor modeling, which I will explain in a minute. Another challenge is that the locations or times of outdoor air pollution measurements and health assessments often do not match, a problem called spatial or temporal misalignment. This is a map of Harris County in Texas. We are interested in assessing the effects of traffic-related air pollution exposures on birth outcomes. By the way, traffic-related air pollution exposures are unobserved source-specific exposures and need to be estimated based on monitoring data. Here, the red triangles represent the locations of monitoring stations, measuring ambient concentrations of many volatile organic compounds, VOCs. I'll show you the data in a minute. The green dots represent the residential locations of mothers at the time of delivery. We have to estimate exposure to unobserved traffic-related air pollution at all of these residential locations, not just at the locations of monitoring stations. Apparently, there is a spatial misalignment problem. Okay, this is an example of VOC data from one monitoring site. VOCs are pollutants like benzene, ethane, propane, toluene, etc. They are ozone precursors. Here I listed only 17 species, but as a matter of fact, more than 100 VOC species are measured every 6 days from canister. This plot shows the time series of concentrations of 3 of those VOC species. And this plot shows concentrations of those species measured from another monitoring site. In most of the previous studies examining the health effects of source-specific air pollution, source-specific exposures were estimated based on data from a single monitoring site. And then, spatially constant monitor-specific exposures were assigned to all participants living in the study area. However, source-specific exposures estimated from a single monitoring site are subject to non-ignorable measurement errors resulting from spatial misalignment between exposure and health outcome data. In this presentation, I'd like to show you how we can utilize multi-pollutant data from these multiple monitoring stations for estimating spatially varying source-specific exposures and how the resulting exposure estimates can be used in health effect evaluation. So, the main objective of this study is to predict source-specific exposures at any location, monitored or not, and estimate health effects associated with those spatially varying source-specific exposures. First, let's talk about source-specific exposure assessment. There are two different ways of estimating source-specific exposures. One is based on deterministic air quality models, such as dispersion modeling, and the other is based on multivariate receptor modeling. Dispersion modeling is a bottom-up approach based on detailed information on the sources, and multivariate receptor modeling is a top-down approach based on observed pollutant data without requiring detailed information about the sources. It's an air pollution forensics method based on a Sherlock Holmes approach. Using the evidence gathered at the receptor, we find chemical fingerprints and identify the corresponding pollution sources. There are two key quantities of interest in multivariate receptor modeling: source composition profiles and source contributions. Source composition profiles correspond to chemical fingerprints for pollution sources. Environmental engineers can identify the pollution source types based on those chemical fingerprints. Source contributions represent the amounts of pollution coming from each source type, and they correspond to source-specific exposures in air pollution epidemiology. The fundamental assumption in multivariate receptor modeling is chemical mass balance, which states that the measured concentration of chemical species at the receptor site is the sum of contributions from independent source types. For instance, the zinc concentration measured at a site can be considered to be the sum of contributions from several sources, such as smelters, incinerator, and automobiles. However, smelters emit particles other than zinc. So the atmospheric concentration of zinc from smelters can be considered to be the product of two cofactors: the percent zinc in smelter particulate emissions and the mass concentration of smelter particles in the atmosphere. Based on the chemical mass balance assumption, the basic model for multivariate receptor modeling can be expressed as follows. Your X is a data matrix, T is the number of time points, and J is the number of pollutants measured. Your Q is the number of major pollution sources, P is the source composition matrix, A is the source contribution matrix, and E is the error matrix. Here, each row of P corresponds to a source composition matrix, which is a chemical fingerprint for the source that I just mentioned. And each column of A corresponds to source-specific exposures over time. You may find that this model looks very similar to a factor analysis model in the sense that only X is observable and both A and P are unknown parameters to be estimated. Here, A may be viewed as a factor score matrix and P may be viewed as a factor loading matrix. But there is an important difference. Unlike usual factor analysis models, A and P are subject to non-negativity constraints because they are physical quantities. These non-negativity constraints are crucial, and we can view this model as a non-negative factor analysis model. Even with additional non-negativity constraints, the usual challenges in factor analysis are encountered here. The number of pollution sources Q, which corresponds to the number of factors in factor analysis, is often unknown. And even under the assumption of known Q, the model is not identified in the sense that model parameters are not uniquely defined. The model with parameters A and P is equivalent to the model with parameters A times R and R inverse times P for any Q by Q non-singular matrix R. This type of model non-identifiability is referred to as factor indeterminacy in factor analysis, or rotational ambiguity in the receptor modeling community. To overcome this model non-identifiability problem, we need to enforce additional constraints called identifiability conditions on the parameters. Although there could be infinitely many different identifiability conditions in principle, not all of them make sense in the receptor modeling context. Because identifiability conditions are additional assumptions on the source composition profiles or contributions, it's important to select physically meaningful conditions rather than purely mathematical conditions. Here are the examples of identifiability conditions often used in multivariate receptor modeling, and they can be expressed as additional constraints in P or A. Among these conditions today, we will focus on pre-specification of zeros in P, which basically assumes that each source profile has some absent species or very minor species. Here I'm using the term species and pollutants interchangeably. The conditions for pre-specification of zeros in P are the same as those often used in confirmatory factor analysis to remove factor indeterminacy. The P matrix here is an example of the source composition matrix with the pre-specifications of zero identifiability conditions. In condition C1, zero elements correspond to absent species in each source profile. Condition C2 implies that no two sources can have exactly the same set of absent species. And condition C3 is a normalization constraint to eliminate the multiplication of a row by a scale constant. Typically, in real analysis, Q is often unknown, and which identifiability conditions are appropriate, for example, where to assign zeros in P for the given data, is also unknown. Those are the main sources of model uncertainty in multivariate receptor modeling because each possible combination of Q and identifiability conditions defines a different model. One solution is to employ a Bayesian approach, which considers posterior model probabilities or marginal likelihoods for several candidate models to deal with this model uncertainty, which we proposed back in 2002. Unfortunately, the model uncertainty problem in multivariate receptor modeling is often ignored in practice. Let me briefly talk about the state of practice approach in multivariate receptor modeling called positive matrix factorization, or PMF. It's EPA software that is currently most widely used by environmental engineers for source apportionment. It's a weighted least squares approach with non-negativity constraints on A and P. And in PMF, Q is estimated by a rule of thumb method, and identifiability conditions are typically not enforced in model fitting. Although PMF is a good exploratory analysis tool, the solutions from PMF may still be subject to factor indeterminacy. I want to emphasize that using no identifiability conditions or inappropriate identifiability conditions in estimation may lead to parameter estimates that are far from the true quantities. This figure shows the principal component plots of the simulated data, the true source composition profiles, and the estimated source composition profiles obtained with and without imposing identifiability conditions. The plots on the left show the estimated profiles imposing appropriate identifiability conditions, and the plots on the right side show the estimated profiles without imposing any identifiability conditions. Here, blue dots represent data points, and triangles are true source profiles, and the stars are estimated source profiles. We can see that the source profiles estimated incorporating appropriate identifiability conditions give a very good approximation to the true source profiles, whereas the source profiles estimated with no identifiability conditions indicate the problem of factor indeterminacy, even when the data contain no measurement errors. Now let's talk about some statistical approaches. For the past 2 decades, several statistical approaches to multivariate receptor modeling have been developed by statisticians, both Bayesian and non-Bayesian approaches. But almost all of those approaches were developed for the data from one monitoring site under the assumption of known number of sources, Q, and known identifiability conditions. The first statistical approach for modeling multi-site multipollutant data and predicting source contributions at an unmonitored site was a geostatistical approach, assuming a multivariate Martin covariance model for source contributions, which was developed in 2013. However, the non-negativity constraint of source contributions was not incorporated into modeling, and uncertainty estimates for source contributions could not be provided. The first spatial multivariate receptor modeling for predicting source contributions along with their uncertainty estimates at any location is Bayesian multivariate receptor modeling, BSMLM, developed in 2018. In BSMLM, the assumption of the known number of sources and known identifiability conditions was relaxed, and non-negativity constraints on source contributions as well as source compositions were also incorporated into estimation. Let me briefly describe BSMLM. Now, the data have both spatial and temporal indices because we have data from multiple locations and locations. We modeled source contributions by a smoothly varying spatial process satisfying the non-negativity constraint using discrete process convolution models. More specifically, spatial temporal source contribution process A can be modeled as a sum of the discrete underlying processes G following a truncated multivariate Gaussian process located at L spatial locations defined on a grid covering the spatial domain, smoothed by the kernel for spatial interpolation. Parameter estimation was performed by Markov-Chain Monte Carlo methods, and for prior distributions, we assumed a truncated matrix normal distribution for GT, truncated multivariate normal for free elements of P, and inverse gamma for diagonal elements of error variance matrix. Then the joint posterior distribution can be simulated by gap sampling. To deal with model uncertainty caused by the unknown number of sources and identifiability conditions, we considered a range of plausible models constructed by varying the number of sources and identifiability conditions instead of a single model, and used Bayesian model comparison based on marginal likelihoods. We performed the estimation of marginal likelihood simultaneously with parameter estimation by MCMC using an efficient algorithm computing marginal likelihoods based on a single posterior sample for each model. I'll skip the implementation details here. If you are interested, we can talk later, or I can send you the paper. Let me show you the application of BSMLM to the VOC data collected from 9 monitoring sites during 2003 to 2005 in Harris County. As I mentioned earlier, more than 100 VOC species are measured every 6 days. Based on previous studies, we had some ideas about potential source types for the area, so we utilized the prior knowledge in selecting the subset of VOC species that can be used for source apportionment, as well as in building a set of candidate models to be compared. Indeed, the selection of relevant species is a very important first step in multivariate receptor modeling because the inclusion of irrelevant species may hinder source apportionment, although I won't have time to discuss more of that today. For candidate models, we considered 7 different models with a varying number of sources and identifiability conditions. We computed marginal likelihoods for each of the candidate models, and the model with 5 sources resulted in the highest marginal likelihood among those 7 models. This table shows the estimated source composition profiles. Actually, the transpose of the P matrix is shown here. So in this case, each column of the table corresponds to a source profile, which plays the role of a chemical fingerprint for a specific source type. As I said earlier, an environmental engineer can identify the source types based on these source composition profiles, and that's how these source profiles were labeled. These maps show the predicted refinery source contribution surface on 3 different dates. we can see the variations of refinery source contributions over space, as well as across days. Each of those maps plays a role of exposure surface for refinery emissions on a different day. These are time series plots of the 5 predicted source contributions, along with 95% post-ray intervals at an unmonitored location, denoted by triangle in the map. We can see that overall, refinery emissions contribute the most to pollution at this location among these 5 major source types. Note that these source contributions represent source-specific exposure estimates at this unmonitored location, not at the monitoring site. Because we can predict source contributions at each individual residential location, spatial misalignment errors can be significantly reduced compared to using monitor-specific source contributions as exposure estimates. By the way, as you can see here, these maps are rather smooth, partly because there is a limited number of monitoring stations, here only 9. Of course, the true source contribution surface could also be smooth, but if the true exposure surface were more heterogeneous, we wouldn't be able to characterize such small-scale variability based only on the limited number of monitoring station data. To improve the prediction of small-scale variation of source-specific exposures, we decided to explore the option of incorporating additional data sources, such as traffic and land use covariates, into the modeling of source contributions. So we extended Bayesian spatial receptor modeling further by considering a spatial log linear model for source contributions. This is still an ongoing effort, but I can present where we are. After many rounds of discussions and data analysis, we came to the following model for the source contributions in the second level of our Bayesian hierarchical models. Here, Z represents land use regression covariates. Beta represents a covariate effect for the kth source contribution. U represents an intercept. Vk is a temporal random effect. And WTK is a mean zero spatial variation random effect modeled with Gaussian process with Martin kernel. For covariate Z, we considered traffic and tree canopy percentage variable. And by the way, those land use covariate data do not come for free. In fact, compiling those data itself requires a significant research effort. Without those data, the model would not be useful. So let me briefly explain how the traffic volume data, called the annual average daily traffic, has been compiled. The Texas Department of Transportation, we call TxDOT, annually publishes its roadway inventory data containing the annual average daily traffic volumes, AADT, of TxDOT maintained roadway segments. The map on the left shows the roadways in Houston. In the map, the thicker lines indicate heavy traffic segments with high AADT values. The map on the right shows the 500-meter, 1 kilometer, 1.5 kilometer, and 2 kilometer buffers surrounding monitoring stations and the roadway segment included within each buffer zone. The AADT value for a monitoring station can be obtained as the sum of the average AADT values per street within the boundary. These maps show the roadway segments corresponding to the locations of all monitoring stations and the assigned AADT. In the left map, we can see the roadway segments identified by the 1 kilometer buffer of each monitoring site. As we can see from the maps, some of the TxDOT's roadway segments are longer than others, which means the AADT values are constant within the segment. The sum of all AADT values of the rows within the boundary is the total traffic volumes at each monitoring site. The AADT values assigned to monitoring site in Harris County are shown in the right map. Red circles correspond to the amount of average traffic volumes within the 1 kilometer buffer area at each site. Here, bigger circles indicate higher traffic volumes. This process of assigning AADT can be applied to all the participant locations in the health study as well. We also downloaded the percent tree canopy data from the National Land Cover Database and computed the proportion of tree cover within 100, 200, and 300 meter buffers surrounding monitoring stations. We also computed tree canopy around the centroids of a gridded surface, about 3,000 gridded point locations in the Harris County area for visualization purposes. Again, the process of assigning tree cover percentages can also be applied to all the participant locations in the health effect study later. Okay, back to the model. For estimation, we use the following priors: inverse gamma for variances, truncated normal prior for pre-elements of P, normal prior for the intercept, and normal spike and slab prior for regression coefficients of land use covariates. Parameter estimation was performed by MCMC, which was a demanding task, and Chang-Woo Lee did all the heavy lifting with that. The major difficulty was with unloading the source contribution matrix A, and he came up with the idea of using auxiliary gradient metropolis hastening sampler, and it worked. We performed simulations, which I'm not going to present today. We are now validating the methods using a real test data set consisting of VOC data obtained from another set of monitors called AutoGIS samplers in different locations from the current canister VOC monitoring stations. These plots show the predicted source contribution surfaces for refinery emissions and gasoline emissions by BSMLM and EBSMLM. As expected, the predicted source contribution surfaces by EBSMLM show more heterogeneity over space, reflecting a better characterization of small-scale variation that may exist in the true source contribution surfaces. As I mentioned, for validation of EBSMLM, we are using a separate set of data. This green triangle represents a new location, channel view AutoGIS monitoring site, which was not used in the model fitting. In these time series plots, the red line represents the source contributions estimated by multivariate receptor modeling using the AutoGIS data at the channel view site, which may be considered reference values. I'm calling them reference values rather than true source contributions because those are also subject to uncertainty, but let's ignore that for now. The blue lines is the posterior predictive median from EBSMLM prediction, and the blue ribbon represents the 80% posterior intervals. As you can see, overall, the trends in blue and red lines are similar, and red reference values are not outside the 80% posterior intervals too often, which is encouraging. We'll continue to elaborate and validate the enhanced BSMLM method. Now, let's talk about source-specific health effect evaluation. Recall that we want to estimate the effects of traffic-related air pollution on birth outcomes. We already talked about the spatial misalignment problem. Also, the source-specific exposure estimates are subject to prediction uncertainty. Even at the monitoring location, those are often the main sources of exposure measurement error. Generalized linear models are typically used for health effect assessment. Let's use STAR to denote the location of participants in the health study and denote the health outcome by Y and the covariates by Z. Because birth weight is a continuous variable, we use a normal linear model. Here, the exposure variable is source-specific exposure A, and beta is the key parameter of interest. It is well known that ignoring exposure measurement error leads to biased health effects estimates and incorrect uncertainty estimates. To account for exposure measurement errors in source-specific exposure in estimating health effects, we can use Bayesian hierarchical modeling. This shows a joint model consisting of an exposure measurement model linking measured air pollution concentrations with true source-specific exposures and a health model linking the health outcome Y with true source-specific exposure A. Because of the temporal misalignment issue between the exposure measurement model and the health model of the joint model could not be fitted using a fully Bayesian approach. So we needed to use a two-stage Bayesian approach for model fitting here. In the two-stage Bayesian approach, we fit the exposure model in the first stage using MCMC and use the exposure samples for source-specific exposures at participant locations A star in the second stage health model fitting. Two commonly used approaches in practice are the plug-in approach and the multivariate normal prior approach. The plug-in approach directly uses a point estimate of the exposure samples obtained from the first stage as a predictor, which ignores prediction uncertainty in the exposures. The multivariate normal approach uses n sub y dimensional multivariate normal distribution. Here n sub y is the number of participant locations, with sample mean M and sample covariance matrix S of A star exposure samples as a prior distribution for A star, and update A star along with other parameters in the second stage. Although the multivariate normal prior approach is known to perform well in terms of accounting for spatial exposure measurement error, it comes with a significant computational challenge when the number of participant locations n sub y is large, because it involves sampling from the full conditional of A star, which is n sub y dimensional multivariate normal. When n sub y is 40,000, as in our case, it's practically impossible to implement the multivariate normal prior approach. To address that issue, we developed a sparse multivariate normal prior approach as a scalable alternative to the MVN prior approach. The key idea is to use a multivariate normal prior with a sparse precision matrix obtained from the Betia approximation that well approximates the original multivariate normal prior. Because the full conditional of A star also has a sparse precision matrix, we can sample A star using the existing scalable multivariate normal sampling algorithms. The details can be found in the following paper, which was just published. We applied our sparse MVN prior approach to Harris County birth outcome data to investigate associations between birth weight and traffic-related air pollution exposures, gasoline source-specific exposures, and NO2 exposures. Recall that NO2 exposures are pollutant-specific exposures. Although NO2 has been used as a surrogate for traffic-related exposures in the past, NO2 is also contributed by other non-traffic related sources. And we included NO2 just for comparison purposes. Gasoline source-specific exposures were estimated by BSMRM, and NO2 exposures were estimated by the discrete process convolution model. We estimated average exposure over the entire pregnancy period for each participant as the exposure metric. And to account for potential confounding, these covariates were also included in the health effects model. Here are the maps of the predicted exposure surfaces for NO2 and gasoline source-specific exposures. This table shows the analysis results for estimating the health effects of NO2 exposures and gasoline source-specific exposures on birth weight. The health effect estimates from 4 different analyses plug in by non-Bayesian and by Bayesian analysis, independent normal prior that ignored spatial correlation in exposure estimates, and sparse ambient prior accounting for spatial exposure measurement error, including spatial correlation in exposures. Uncertainty estimates are given at standard error or posterior standard deviation, and 95% confidence or credible intervals are also shown here. Here, all four analyses suggest statistically significant negative associations between exposures and birth weight that are similar in magnitude. As expected, compared to other approaches, the sparse ambient prior approach leads to larger uncertainty estimates for the health effect parameter, which is a natural consequence of accounting for uncertainty and spatial correlation in the exposure estimates. Okay, let me summarize. Spatially extended Bayesian multivariate receptor modeling approaches, BSMLM and eBSMLM, can predict source-specific exposures along with uncertainty estimates at any location, which can reduce spatial misalignment error. Especially, eBSMLM improves the characterization of small-scale variation of the source contribution surface by incorporating land use covariates into modeling. This may further reduce exposure measurement error in health effect evaluation. It's important to be aware of the underlying modeling assumptions for source-specific exposure assessment, such as the number of major pollution sources and unknown identifiability conditions, and check whether those assumptions are reasonable. We also proposed a scalable two-stage Bayesian approach, utilizing a sparse multivariate normal prior based on a Vecchia approximation for accounting for exposure measurement error in health effect evaluation. The proposed two-stage Bayesian approach can be applied to any predicted exposures, including both source-specific exposures and pollutant-specific exposures, as long as the exposure estimates along with their uncertainty information are available. Finally, a work in progress. We are currently working on examining associations between source-specific multipollutant exposures and risk of stillbirth in Harris County. We are also assessing the impact of mandatory reduction of vessel fuel sulfur content in the North American emission control area on shipping-related air pollution and total and cause-specific mortality and hospital admissions for Harris County residents. This requires advanced source apportionment to separate shipping emissions from other sources and also causal mediation analysis. Also, I am currently collaborating with Raj, Sam, and Matthew at the A&M Statistics Department to further extend Bayesian spatial multivariate receptor models by incorporating satellite data to improve the prediction of intra-urban source-specific pollution exposure. I'd like to close by citing these two famous quotes. An approximate answer to the right problem is worth a good deal more than an exact answer to an approximate problem. All models are wrong, but some are useful. I heard these quotes when I was a graduate student at A&M, and at that time, I did not really understand what it meant. But after working on real problems for 25 years, I think I began to truly understand. Whenever I start a new project or collaborate with other scientists and engineers, I strive to learn as much as possible about the subject matter and ensure we are solving the right problem, and our models are useful for them. Thank you. I'll stop there.
Thank you, Dr. Park. That was a very fascinating talk on a real-world problem. I think we're all faced with the effects of pollution. So very interesting to see how you have used your training and education and experience through the years to solve some of these problems. We have several people in the audience today. Does anyone have any questions or comments that they would like to address to Dr. Park? Quiet. We have plenty of time if anyone has any questions or comments. Gotta thank you. Last call for questions, comment. Look like that anyone has any questions or comments. Oh, hang on. From Daniel Posner, do you have any guidance on the initialization of parameters in your models? I often struggle with the spatiotemporal. Sorry, I can't see it all. My Zoom menu here.
Okay, when you say initialization of parameters, you mean during the MCMC implementation?
Correct.
Oh, yeah, it actually depends on the model and context. I mean, in my case, I mean, even using the random, matrix as the starting values work fine for me as long as they satisfy the basic constraints. For instance, some non-negativity constraints. I mean, for matrix P, I usually use uniform random numbers. And of course, you can, start from a, good, more informative starting values from MLE or whatever. But in my case, I mean, of course, it could help with faster mixing, but just the general starting values work for me. So I think it really depends on the context that you are working on, the models. I mean, probably you are not asking about these receptor models, right?
Right. Yeah. No, hierarchical models in general, the Bayesian hierarchical models. Just sometimes we have too many levels, and you can get tripped up trying to set the
Yeah. I mean, if the mixing is an issue and the convergence is a problem for faster mixing, of course you can explore the good starting values, but it was not really an issue for me. Yeah, so far.
Thank you.
Anyone else with questions or comments? There's a couple other comments. One person seems to be working on a similar problem, is looking forward to reviewing your articles.
Oh.
So that'll be interesting. Perhaps we'll reach out maybe.
Yeah, let me know if you need my paper. I can just email them.
Yeah, awesome. Well, thank you very much, Dr. Park. Obviously, oh, hang on just a second. We have another comment. Oh, this is directed to Daniel. Daniel, I don't know if Daniel sees that comment from Chang Wu Li. Yes, he does. Awesome. Well, again, thank you, Dr. Park. I appreciate your time today and sharing your experience with the group. This is always very useful to see what our graduates are doing in the real world to use their statistics. So I wish everybody happy holidays coming up. And anyone who is interested in presenting their work to the SFSN, please let me know. We always looking for speakers to share their insights and their experience with statistics. So thank you very much, everyone. Have a great day.
Thank you.